We can synthesize complicated events by combining simple events whose probabilities we already know. To demonstrate this, let's let E and F be events in an experiment with a sample space S. There are three operations we can perform on these sets. We can take their intersection, which corresponds to a new event in which both an E and F must occur. We can take the union of the sets, creating a new event in which either F or E or both occur. And finally, we can take the complement of a set, which is an event in which E does not occur. Now, the keywords in each operation are and, or, and not. And while these have formal mathematical meanings, you probably already have a good feeling for what these should do. To make things more concrete, let's set up an example. So let's suppose that you roll 2 fair d6 and define the event E such that the first dice is odd, and define the event F such that the second dice has a value of 5 or more. The intersection of E and F is the event that both the first dice is odd and the second dice shows a value of 5 or more. Both conditions must be true, neither of them is optional. Their union is the event either the first dice is odd or the second dice is 5 or more. One or both of these conditions must be true. And finally, the complement of E is the event that the first dice is not odd. Or if we wanted, we could just say something like the first dice must be even. So how do we compute the probabilities of these new events? So certainly we could just compute the intersection, the union, the complement explicitly, and find the probability that way. But our goal is to find an easier way, assuming that we already know the probability of E and the probability of F. So starting with the intersection, we can ask if E and F are independent events. When we defined independence, we talked about two experiments being independent rather than two events being independent, but nonetheless, the same reasoning does apply to events as well, thought of as their own little mini experiments. If the events are independent, then we can just multiply their probabilities per usual. While if the events are not independent, well, for now we'll just have to compute the intersection manually, but we will see another technique once we've learned a little bit more about conditional probability. In our example above, we can just write out the intersection of E and F by hand to get the following. Now the dice are fair, and this event has 6 outcomes, so the probability is 6 over 36. But on the other hand, these events are also independent, so we can compute them in a different way. Let's think about this. So the first dice being odd has no effect on whether the second dice has a value of 5 or more, right? They're completely unrelated. So we can multiply their probabilities, and if we do that, the probability of E is a half, while the probability of F is 12/36, so their product gives us 1/6 as we expected. Moving to the union, well, this time we have to be a bit more careful. We are tempted to just add the probabilities together, but we must account for the possibility that we've double counted some of the outcomes. Thus, the probability of the union is the sum of its parts less the probability of the intersection. Now, this last part here takes care of the double counting problem. When we actually do an example, I'll illustrate this a little bit more completely just in case you don't see it right now. Something else that we get immediately is that if E and F are mutually exclusive, then in that case the probability of the union is actually just the sum of each event. Okay, so returning to the example above, we know that the probability of E is 18/36 and the probability of F is 12/36. We also computed the probability of the intersection just a second ago, and if we combine all of this information, it gives us the probability of the union, which we can work out to 2/3. Okay, so this is a great example to actually illustrate what I mean by this double counting problem. Let's draw up our dice roll table with the first dice being along the first row and the second dice along the first column. I'll write in E for the events which occur in E, and unsurprisingly, I'll use F for those events in F. Now, if you count how many objects we filled in, you would get 24, which is the result above, right? 24 over 36. But if you count out the E's and F's separately, we get 30 of them, which is 6 too many. So what went wrong? Wherever you see an EF together, that counts as a single item in the probability, but it was counted twice, once as an E and once as an F. Therefore, we have to account for this by subtracting one copy of the overlap, which just has the same size as E intersect F. Okay, finally, let's compute the probability of the complement. Now to do this, we're going to need to recall a few facts, namely that E and its complement give us the entire space, and that E and its complement are mutually exclusive. Now the probability of S, that anything happens, is equal to 1. And if we write S as the union of E and E complement and apply our formula for the probability of the union, then we get this, which says that the probability of the complement is the complement of the probability. And this should make sense, right? If there's a 1 in 3 chance of something happening, that means there's a 2 in 3 chance of it not happening. Okay, so I want to use a different example than the dice rolling to illustrate this, just so we can see why this might be useful. So let's suppose that you have 15 balls in a bag, and each of them are numbered 1 through 15. You're going to choose 2 of those balls without replacement. What is the probability that the difference of the 2 balls is not equal to 8? Now, if you think about this, most of the time the difference won't be 8, which means we'd have a lot of counting to do. And if instead we think about the dual problem, how many times will the difference be exactly 8, we have a much easier problem to solve. So let's take E to be the event that the difference is exactly 8, and let's find its probability. Since there are so few possibilities, we can just write them all out, like so. Now there are 7 events in E, and 15 choose 2 ways of picking 2 balls from the 15 balls, giving E a probability of 1/15. Well, now what we're really after is the complement of E though, and the likelihood, which is the likelihood that the difference is not 8. So if I subtract 1/15 from 1, that gives us a probability of 14/15, and that's exactly what I was after.